Okay, this is the second part of the lecture that we did last time, which was covariant differentiation on submanifolds of Rn. So if you recall, last time we were doing how to do covariant differentiation on submanifolds of Rn. So if I quickly recall the main contents of the last lecture, so what we did is that we defined covariant derivative is the tangential component of a derivative of a vector field along a curve. So finally we came with an equation, and that equation was that covariant derivative, this capital T is representing the covariant derivative, this is equal to summation partial bk partial t, where bk is a component of the vector field y, plus summation is over k, gamma k ij and bj, and then there is fk. And there is also aj duj by dt here. So let me write it like this. Duj by dt multiplied by ai, and then this becomes fk comes here. So we have explained these things in very detail in the previous lecture, and there we saw that actually if this is the manifold, you can, for more details, you can watch the previous lecture. Let me say that this is a part of the manifold. So if we have this point, so there will be tangent plane at this point. Say this is the tangent plane. So there will be the basis vectors for this tangent plane, such as f1, f2, etc. and so on. In general case, there will be n basis vectors. So then any vector in this tangent plane can be represented as a linear combination of these basis vectors. And now if we have some vector field y in this tangent plane, TPM, so I can represent that vector field by summation bk. It is better to use the Einstein notation, so we get rid of this summation symbol. So then this yk will become bk into fk. So this will be any vector field at point P. Let me say if I am concerned with point P, so then this will be just at point P. Now for taking the covariant differentiation, last time you discussed this, that we take a curve over here. Say I take curve over this manifold, I represent this with P of t, and then I differentiate along this curve. So if this is some vector field y, then this y is actually at each point of this curve. This vector field is defined in the tangent plane, and we take the rate of change of this vector field dy by dt along this curve. So this y is actually a function of this p of t. So it is taken along this curve. And then we take the tangential component of this, which is represented by pi prime. So we call that the covariant derivative. Now, by looking carefully at this formula, what we can see is this, that for finding the covariant derivative, we need to define a vector field along some curve, such as this curve over here. And then you take the derivative. So these components of the vector field are actually the functions of t along this curve. And we also know that actually in manifolds we do this coordinate mapping. So for example, this manifold is actually mapped with some Rm, and we label these coordinates with u's, u1, u2. So if I consider a small part of this, so it is mapped over here. And similarly here will be unit vectors, partial u1, partial u2. And the map from here, from the manifold to this Rm is phi. We have done this in detail in the last lecture, so you can view that lecture for further details. And this is phi inverse. So phi is actually a diffeomorphism between Rm and the manifold. And phi inverse is actually from Rm to the manifold. So what is phi inverse? So phi is actually from manifold to Rm, is Euclidean space, and this phi inverse is actually from Rm to manifold. So we have this type of situation over here. And then this phi inverse in the form of components is in this manner. It is actually consisting of g1, and g1 is actually a function of u1 to um. Similarly, g2, it is a function of u1 to um. And similarly up to gn. If this manifold is embedded in Rn, then there will be up to gn. And all of these are functions of these local coordinates. So now this Christoffel symbol was also defined last time. This is gamma kij. This symbol gamma kij. So this is actually gamma kij is actually partial square g partial ui partial uj and akl. So this is from the previous lecture. Now what we will do in this lecture is to further study this, And now we change our point of view slightly from the previous point of view. So previously we were taking the vector field along some curve, while here what we will do is to define this thing, the covariant derivative of, so let me, is now we are starting today's topic. So let me draw this line here. That was a quick revision from the last video. For details you can check the previous video. So now we want to study covariant derivative at a vector field x at point P of vector field y, del xpy. So this is our notation on submanifolds of Rn. Submanifolds of Rn. Okay, so how we change our point of view over here? So let us say if this is the some part of the manifold, and we are taking this point. So last time on this manifold we were taking this curve, and we needed to define this vector field along this curve, and only then we were able to differentiate or take the covariant derivative of this vector field y. Because this part of the derivative, partial bk partial t, this requires us to know the vector field y also at the nearby points, and for that the curve is necessary. So in order for this formula to work, this taking this curve pt is necessary. Now we want to get rid of this, and so we change our point of view. So how we do this now? Let me say I'm having some vector field on this manifold M. This is the M manifold. And on this manifold we have tangent space at each point. Say this is the tangent space at this point. Now in this tangent space we have vector fields which I need to differentiate. So let me say I am having this vector field y over here, and this is lying inside this tangent space of M, TPM. Also I have another vector field here which is in this direction, xp, and I call this xp, vector x at point P. Now this is point P of the manifold, and definitely in the corresponding diffeomorphic Euclidean space Rm, there will be the corresponding coordinates u1, u2, etc., and there will be a mapping phi, and then there will be a mapping from here to manifold, that will be phi inverse, and that this will be actually a diffeomorphism. Now for this point P, I can have several curves, and the derivative and this xp vector will act as a tangent vector for those curves. So let me say I have some curve. Let me say this point P is actually P belongs to M, and this is actually obtained from phi inverse of these coordinates u1 0, u1 naught, u2 naught, etc. I obtain it from the phi inverse of some points over here. So I can say that these are the corresponding points in the diffeomorphic Euclidean space. Now I can take a curve, any curve, whose initial point in that curve will be also here and also there in this space. So P of phi inverse of Pt naught will give me this P point over here in this manifold. Now this curve, this vector xp can be represented in this manner: summation aj and fj, where fj's are actually the basis of the tangent space. These are the basis vectors of the tangent space. And these are constants because this is a single vector, so it will be constant at this point. Now this xp vector is actually the push forward of the vector at point t naught here in this Rm space. So I can push forward phi star inverse this vector aj partial uj. So, and this will give me aj because this push forward is linear, so aj will come outside, and this will give me so as they are diffeomorphic, so xp can be also written in this manner because it is actually the same vector taken from here, from this space. So the push forward is there in the tangent space. So because it is a constant vector, so this will become, I can write this xp in this manner also: aj partial uj, or also in this manner partial uj aj. So what I have done up to this point is this, that I took a vector in the tangent space xp, and this xp can be expressed as a linear combination of the basis vector of this tangent space. Since each basis, by definition, each basis vector of the tangent space is a push forward of a basis vector from the diffeomorphic Euclidean space. So I can write this thing xpij fj also in this manner. Now the formula for the covariant differentiation that we had last time, so now we are confined to a single point. So I can write this thing, the formula for the covariant derivative at point P is this dy by dt at point t naught, and I call this del xpy. So this will become if I'm using the Einstein summation, so partial bk, can see here this part of the formula, the first partial bk partial t in this equation, this part will become partial bk partial uj, then partial uj partial t. And when I restrict myself to t naught, so then all these values will be actually restricted at t naught. So this will become, the remaining formula will be same. So gamma kij plus gamma kij, and then you can write this duj by dt also, because this is depending only on this single variable. So gamma kij and duj by dt, and then we have aj over here, ai, and then there is fk. Okay, so now, and all this is happening at point t naught. This is also, fk is also at point t naught. So everything is restricted to a specific point t naught. So this thing will become now I have this notation. So let me write that notation first. I have this notation that if I have some vector field x acting on some function f, so this will become, so this is actually the directional derivative, if you remember. So x is actually what it is, that will be some a j or partial uj, and here will be f. This will become aj partial f partial uj. So we have this notation already. So according to this notation, I can write this in this manner, del xp y will become, okay, what is this part duj by dt? This is actually the component of the vector x along partial uj unit vector. So I need to write it here. Duj by dt is actually aj. So this aj part is actually, because this is coming from the differentiation of the curve, so this aj becomes duj by dt. So if I'm having this curve and I differentiate it, so this curve can be represented by u1t up to umt, and then when I differentiate this curve, so xp will become aj partial uj, and this aj will be duj by dt. So this will be the notation. Okay. Okay, this AI is actually BI. This is BI because this is coming from the vector field Y, and the Y vector fields are represented with B. The components of Y are represented with B. And AI is representing the component of this XP. So AJ is actually duj by dt. So now this del xp will become, I can write this in this manner, partial bk uj, and this duj by dt, this part will become aj plus gamma k ij, and this duj by dt, this will also become aj will come, and bi will come. And all of this is actually at point P, or at time t naught. So del xp y will become, now following this above notation, this notation ai partial aj partial ujf, I can write it as xf. So this will become, as I am restricted to only a single point, so this will become xp bk and plus gamma k ij and bi aj then fk. Okay, so what is the meaning of this formula? If I write also the summation here, so actually the summation is over k and I and j. So this formula can be written in this manner: del xpy summation k xpbk plus double summation gamma k ij and pi at point u naught, aj at point u naught, and then fk. So this is the formula that we obtain. This is the formula that we have. Okay, so what is the difference between this formula and the previous formula? In this formula, we need to specify only a single vector at a point in the tangent space. So that single vector is actually xp in the tangent space, as we have done here. And then we need to differentiate this vector field y along this tangent vector xp. So for that we have this notation del xpy. And you can see that in this part we don't need to take any curve along which we do differentiation. We just need to specify this vector field vector tangent vector xp at a point, and then we can do differentiation along that. This summation is actually over I and j. So this is the beauty of this formula, because we don't see anymore this expression for partial bk partial t, which requires bk at different points. So now in this manner I can say that this del xpy, the covariant derivative of y vector field along xp, is actually a map del xp y. This is a map from the tangent space. It takes two vectors, one is from the tangent space and the other is from the vector field on the manifold, and it gives us a vector in the tangent space. So that is this Vm is vector field on the manifold. So this is actually vector field on the manifold. So now we want to study some properties of this mapping. Properties of del py, or we can form a theorem, some theorems regarding this which have very simple proofs. If xy are vector fields on submanifold of Rn, and these are CR vector fields, which means they are R times continuous, then this del xy at point P, which is equal to del xp covariant derivative of y at point P along x, is CR minus 1. And that is because it will be differentiated once, so the degree will reduce. So if the previous one was, let me say, C3, so this will become C2, del xpy will be C2. The second is that this map del xpy, which is actually from TPM cross vector field on M to TPM are linear in both x and y, which means this property, this is very important. It means that del x1p plus x2p y is actually del x1 p y plus del x2 p y. Similarly, del lambda xp y is equal to lambda del xpy. And also del xp y1 plus y2, we say alpha beta. This alpha beta are real number, similarly lambda is a real number. So this will become alpha del xp y1 plus beta del xp y2. So these are, it means that this linear mapping is actually linear in both of its arguments. Similarly, it is also linear, C infinity linear in the x argument. So let me say if I have this type of situation, so this is only obeyed by x, not by both x and y. So it has, I can call this function linearity, C infinity function linearity in xp. So for example, if I have some function f and I multiply it with xp and then I take the covariant derivative, so this becomes f del xp y. Okay, what is the fourth property? The fourth is this. You can very easily verify this. So it is not linear with functions along the y argument. So if you have this type of situation, fy, where then this will become xpf xpfy and plus f del xpy. So this is these are some properties. Similarly, the fifth property is this. You can very easily verify all these properties. This is a very simple exercise. If xy belongs to the vector field on M, then this Lie bracket of x and y will become equal to del xy minus del yx. And what is this xy bracket? Let me say if x is this, ak partial xk. Here this is the basis, and y is bk partial yk. So then this xy will become equal to ak, and the application of x on y first. So and then partial xk on y, and minus then bk partial yk on x vector field. So this is actually equal to this thing. The sixth property is this one. xp inner product of y1 and y2 is equal to y1 and y2 have inner product, and we applied this vector xp on this. So this will become covariant derivative of xp along y1 y2, and then inner product plus y1 and del xp y2. So this is the, so these are some properties of this linear mapping or this covariant derivative at a point of a tangent space. So all these properties arise once we start doing things along this vector xp. Okay, so we stop here.